Hello, welcome once again to another edition with Special Maths. So we'll be looking at the problem corner for the month of February 2021. And the first problem, the geometry problem. So start off with the warm-up. All right, so we have right angle triangle ABC, right angle at A, and we have D and E, two distinct points on line BC, where B, C, D, and E are all distinct. So we let the circumcircles of ABD and ACD meet again at F, and let the circumcircles of ABE and ACD meet again at G. And finally, we let the circumcircles of BDG and CDF meet again at H. The question is, how many cyclic quadrilaterals do we have? So to do this properly, let's go over to the GeoGebra app and look at the construction of this. Okay, so we have right angle triangle. Let's just quickly construct that. So I'm making use of a semicircle here. Okay. So let's start it over. So we have A, we have B. Okay, so just drawing this line here and draw perpendicular at A. Okay, then we'll just pick C along that line. So somewhere here. Join this. So we now have BC. Okay, so pick two random points. So I'm just going to place them, let's say, here. And we draw their circumcircles of ABD. So, okay, ABD and ACE. So then we also have ABE and ACD. That meets this at D. So we have F here and we have G. All right, so H now is the intersection of BDG and CDF. So B, D, G, and C, D, F. Okay. So the second point of intersection of this, and that's H. Okay, so this is a construction we need. So we want to find all the cyclic quadrilaterals. So far we already have a number of circles here. So to create each of the points F, G, and H, we had pairs of circles. So altogether we have 6 circles. So so we have 6 circles so far, or six cyclic quadrilaterals so far. Okay, so but want to see if we could get more. All right, so okay, so before we get more, what I'm going to do is I'm just going to color the ones we had from the beginning so that we don't misplace them with other circles that may popping up. So we have 6 of them here now. Okay, so from the diagram, you might be able to guess a few. So probably there's some kind of symmetry going on. So let's analyze like what are the possibilities when it comes to the circles, so that I don't end up missing anything. So to do that, first of all, we're going to analyze how many circles could we have maximum. So we just want to find an upper bound for those circles. So how we're going to do this is, first of all, it's not hard to observe that no three of them, like no five of them are cyclic. So we can prove that, but I'll not be going into that detail now. So I'm going by that assumption. So if you pick 2 points out of the 8 points we had there, let's say A and B, right? Then by picking any other 2 points from the remaining 6 points, we get possibly a cyclic quadrilateral. So let's say D and F, which we already had. Now, what are the possibilities here now? If we have D and F, the argument here is that we cannot have D and something else, because if we have D and let's call it something else, let's say X, then A, B, D, F, X would all lie on one circle. So we'll have 5 points on the circle. So it doesn't work like that. So if we already have D and F pairing up, then we can't repeat any of this. So we see that we also have G and E. So we can only have like from the 6, we can only pair them up in once in only 3 ways, right? You can only pair them up in only 3 ways. You can't have any other one coming in because they'll be some repetition somewhere, creating 5 points in a circle. So every 2 points, for every 2 points, we have 3. So that gives altogether 8 choose 2 times 3 circles. But if we have A, B, D, F, it's going to be the same circle as if we had started with AD and somehow we wrote BF as well. So there'll be some repetitions, which just be matter of kind of like a permutation of these. So basically, it's just a matter of which ones we chose to start with, and then the other two will follow automatically. So this is just from the 4 of one same circle. That gives 4 choose 2. That gives 4 choose 2, which is equal to so we could just write this like this. By canceling 2 from both methods, we get 14. So that maximum of 14 possible circles we could have. Maximum of 14. So so far we already had 6. So possibly they might be up to 8. Maybe not. So before we go into what those possibilities are, there are some we'd actually get almost right away. So this might be very useful. So we have right angle at A. So if we call this, let's say angle B, and you call this angle C, so you have B plus C is 90 degrees from some of angles in the triangle. So that gives that if we draw this line here and you extend this, then from circle A, B, D, F, this will also be B, and from the circle AF, EC, this will also be C, and that sums to 90. So what this brings is that we get 90 at F, and also in a very similar way. So if you look at join this line A to G, look at D, D, GA and AGE, then what you see is that from circle ADGC, that this will be exactly angle C, and in a similar fashion, this will be exactly angle B, which also sums to 90. Okay, so we have 90 there as well. And so with this, you might have a suspicion already on what this would be. Okay, so let's see how we can get it done. All right. So what we could use to connect this, we could just use um, we could use this here. Okay, let's see how this goes. Or rather, okay. So rather than that, we could go with something else. But for the meantime, let me erase all this. So we have 90 degrees at each of those parts. So let me update that in the diagram. So we have this is 90. This is also 90. So let's get that angle measurement. We have 1, 2, 3. That's 90. This is also 90, and we have 90 here. And this 90 degrees actually naturally forms circles. So what we want to do now is to get probably another circle. But at least this gives us some ideas of the kind of circles we'll be expecting. Okay. All right. So to get this one, there are different ways you could try to go about it. So we could use this here. Okay. So what we're going to do, let's exploit symmetry in this case. So to make things easy for us, we're just going to exploit symmetry because this whole figure look kind of symmetric. Um, it's A and H kind of replacing each other, and F and G swapping as well. So initially we had 90 degrees at A, and we got that for F. So logically, if we had for F, we could reverse back to getting for A. So in a similar way, if we had for G, we should be able to get for H in a similar way. So we're going to do just how we constructed for F. We drew AF. So in this case, we're just going to draw GF, GH, and we know angle at G is already 90. So what you see now is that this angle here, let's call it alpha, will be the angle here. So this will be alpha, and this other angle here, we call this beta. Okay. So we would want beta to be 90 to be we want this to be beta as well, right? But for this to happen, so we want this to be beta. And the idea is that now alpha plus beta is 90, so these two angles will sum to 90, and that will force this to be 90. But for that to happen, we need H, G, E, C to be cyclic. So once we have that cyclic, then indeed we have what we wanted. So now we just try to show that this is going to be cyclic. So let me erase all this now. So once we've shown that that is cyclic, then we indeed have 90 at H. All right, so I want to show that this is the circle. Okay, it's gonna be a bit tough. So what we're going to do is we're gonna try to want to show this is cyclic. We'll try to do some constructions. I guess this one. Let's try to make use of some of the circles we already had. So I want to show. So let's call this theta. Call this phi. So I want to show theta and phi are the same. So that'll make this cyclic, and then we'll have what we need. So I'm just going to call this x. So by placing this angle here, we can now relate these two circles BHFC, DHFC, and also BDGH. So for BDGH, we get x here. and for um, DFCH, so you get this external angle to be x plus phi. Okay, and then now moving from BDGH, we can now go to circle ABGE. So angle EB is now. So if we should draw this, we also get x here. And in fact, theta can also be traced on this circle. So we get theta here. So that's based on segment BG of the same circle ABGE. So we get theta there, meaning we want these two angles, the angle at A and the angle at F here, want them to be equal. Okay. Now we're going to do a different division. So now we have an idea of what we want to do. So I'm just going to erase some of these lines to make things better. Let's erase this ones. So we had this. So altogether, this angle at A now is x plus theta. So we're going to break it up in a different way. So we're going to break it up to involve new circle AFEC. When you draw that here, then you get this plus this is x plus theta. So if we call this y, then what we'll have left here will be x plus theta minus y. And following based on that circle, we get here, based on circle AFEC, we get y here as well. And by looking at triangle DFC, that external angle, we imply the angle at D here would be x plus phi minus y. And indeed, ABDF is cyclic. So the angle at A is equal to the external angle at B. So those two angles should be equal. So we have x plus theta minus y is equal to x plus phi minus y. So theta is equal to phi. So we have what we need. All right, so I'm going to erase all this now. So we have two circles. We have one more circle now, and also we have the angle at. Also, we have the angle at H. So this is 90. So that's 90. And we've also found circle HGEC. Change the color of this blue. So we have, yeah. Then let's draw the last circle that we found. Okay. Yeah, so indeed it's cyclic, makes sense. Okay. From the right angle triangles, we get those 90 degrees will create some natural cyclic quadrilaterals. So far we've added 3 more to our list of circles. So what we're going to do now is to figure out among all those potential circles, which ones are left, and to see if they are going to be circles or not. Okay, so finish this. Now, so far we have 9 circles. So take this 9 circles, and we're expecting generally 14 possible circles. So one circle that is not really going to happen is the straight line BDEC. So this is technically a circle, but it's not really a circle in the context we're looking at. So just keep this in mind. But this means this one is gone. So we have 4 more circles or 4 more possible circles to consider. So let's look. So let's try to go a bit symmetric. So you can see B, just now we had H, we had HGEC coming in, which was kind of like a pair with BDGH. Then a similar way, HDFC will have a pair which will now be BFEH. Okay. And we also have AFGH. Then there is ADHE, and there's also BFCG. Yeah, so this 9 we had before with the straight line and this other 4, those are the possible ones we could possibly have. So just need to check which of these are really circles, which ones are not. So so first BFEH. So we expect this to be a circle, which shouldn't be too difficult now because we have the symmetry is almost kind of complete. So it's kind of similar to what we had ABGE to get angle at 90, the angle at G to be 90. So this in a similar way, we're going to make use of the angle at F. Let's make use of the angle at F and try to use that to show that we have this circle. Okay. So let's see how we can make use of this. Okay, so I want to show that this plus this is 90. Okay, so let's see how we can trace this. I think there should be lots of ways we can go about this. If we call this x, this should be x as well. And the whole of this should be 90 minus x. And that will make the whole of this, the external angle here to be 90 minus x using circle ADGC. And that will mean the angle here, that's EGC, would be x. And tracing that using circle HGEC to get x here. And this was already 90, so that gives us 90 minus x here. So indeed, when we sum the angle at F here, which is 90 plus x, and the angle just we have circle. So this one is good. So we have one more circle at least. So let's update that once more because we could make use of it along the way. So let's update this. That's B, F, E. So that's in the circle. Now we have A, F, G. So it's looking stretchy. It looks like it's also circle. It's almost a straight line, so probably a circle with a very big radius. So let's see. So if we're going to draw that, let me use a different color to like this. So if we draw this, it's very slanted quadrilateral. Okay, so we want to show that this angle here and this angle here sum to 180. Okay, so let's call this our first angle. Let's call this x as usual. So I want to show the other angle is 180 minus x. So what we have now is um, using looking at AH, we can relate this to the circle ABHC. So just going to include this one called Y. Okay. So let's now trace Y all the way back here. So this is Y. And Y plus X now being the angle at H here, we can now connect that to circle BDGH. So D, the external angle at D would also be X plus Y. Okay. Now, when you extend the line AF, then the external angle at F here would be equal to Y using circle AFEC, right? And if you look at GFE, it's also going to be equal to GDE, which is X plus Y, since we have the circle with diameter DE. So GFE is equal to X plus Y, and already had a part of that angle being Y, that external angle at F. So the remaining part is going to be X. And since we have a straight line there, then AFG would be 180 minus X. So yeah, so this gives, this also gives a circle. So we have this working as well. So far so good. We have 11, and it just remains two more to make sure. So AD, okay, let me draw this one. Let me draw this one. So we have AFG. Okay. All right. So now ADHE, ADHE. So for when it comes to ADHE, you see that based on the particular diagram we have, this is definitely not possible. DAE, look at DAE and DHE, right? If you look at these two angles, suppose these were cyclic, they are supposed to, sum to 180. But from this, you see that the angle at A here, just a part of um, the 90 degrees BAC, and the same goes for the angle at H. So BHC is also 90. So these two angles are both less than 90 degrees. So if we sum them, there's no way we're going to get the full sum. In fact, the same actually applies to this one. So the angle at B and the angle at C sum to 180. So these two smaller angles cannot sum up to 180. So they'll be less. So that means these two actually fails. And so yeah. Now just you have to take note that this argument works. This argument works. So we have um, let me erase these lines. So this argument works for this particular configuration. Now let's see if we change. So if we change the configuration, see that most of these circles actually they still remain. But the argument we just made about the angles at B and C stuff, it might not really be applicable in the same sense as what we just did. Okay, so this means if you want to show it in general, you have to do a bit more than that. But I'll just go with this. Just for it, whichever figure you started with, yeah, you could always do similar arguments to this. just to check something. So look at this angle, this angle. So the color. Okay. So you might want to explore to see what's going on. Trace those guys out. So anyway, it's all going to boil down to some of angles not being less than 90. By comparing them to a different circle that's involved with F and G. That's involved with B and C. So yeah, we could go along all those directions. Or you could use a circle AFGH as well if necessary, and do something similar to that. All right, so let's stop the warm up for now. So this means what we have now 11 circles and one straight line, which technically is a circle as well, but we just go with 11. All right, so see you in the next level, level 1, which will be coming up soon. Thank you. Bye.